Well, welcome. This is Terrence Fagan, and I'm going to discuss in this short video about the method of joints and how to analyze them. Why do we analyze them? The internal members of a structure, first and foremost, because that's where a lot of forces are hidden, and we want to figure out how to design with them. So we better prepare for the design itself. So let's begin. And first and foremost, what I'm going to do now is the way we can do this is we're going to look at each joint, or one particular joint. Because it doesn't state, but what I want to do is I want to find the internals of each member. So member AB, member BC, member BC and AB. But once we figure out one, you can look at the other ones, and I'm going to demonstrate how to do so. First and foremost, let's circle what we're going to find first. So first we're going to draw B. So what we can do with B is we can draw a free body diagram of joint B. Now, because these are beams with joints connected, we can know that there's no applied moment, no applied moment to them. So they have to be purely in what's called tension or compression. So with that, what we're going to do is we're going to say that there's B, and then one part of it looks like that, the other part looks like that, and this is telling us it's a 90-degree angle. So right then, I'm going to change the color. I'm going to say this is the weight, or the W. Some weight may be hanging off, or some force of this. And what I'm going to do now is what you haven't seen before. But first and foremost, what I'm going to do is I'm going to put everything in what's called tension. Now I'm going to put the force AB. Also, I'm going to put the force of BC. I'm going to put them both in tension. So the way you know something is in tension or compression is if it's moving away from the joint. The force is moving away from the joint, it's in tension. If the force is going into the joint, it's in compression. But right now, let's just model everything. It's a good habit to get into. Is first and foremost model everything in tension, and if it's negative, what we do is we know it's actually in compression. So what I'm going to do is I'm going to change this a little bit. I'm going to change my axes. So basically I have my x-axis up here and my y-axis here. So that means we can use the sum of the moments and sum of the forces. But sum of the moments actually doesn't give us much because there's no arm length, there's no length r vector here. So we're all stuck with just in plane geometry here. We're stuck with sum of the forces in the x direction is equal to 0, and sum of the forces in the y direction also equal to 0. So if we look at this, and we can break this W down, let's break it down in green here. Let's come up with what we know. So with that, know from this is W x direction, and this is W y direction. And if you notice, what I'm going to do is that alpha is right here. So that's how we can get, and this beta here, this is a theta. If we were to draw this out, would be right here because you add them up and they get 90 degrees. So it's actually a fairly common thing to do. So let's take the sum of the force in the x direction first. So we have negative FAB, right? Because that's the only thing in the x direction, no other internal load. But we also have an applied load, and that is going to be plus this WX. And what the WX can represent is the W, and it would be the cosine of alpha. all that gets equal to 0. Nothing else is in the x direction. So with that said, we can say that FAB is equal to W, whatever it is, times the cosine of that angle. Now you can put numbers in if that helps, but knowing how to model this, knowing the fundamentals to do this, makes your work so much easier. So we're not done yet, but we can put a little underline there, and like I said, later if we decide to put numbers in, you can put numbers in. Now we use the sum of the force in the x direction, and then we use the sum of the force in the y direction for our next step. And we're going to come over here. So we could say the sum of the forces in the y direction is equal to 0. So in this case, we have negative FBC minus, remember that the y is positive up there, minus this WY. But the WY can also be the W times the sine of that same angle, which is alpha. Now we could say also the cosine of theta, it's the same thing. So that gets equal to 0. We can say now that the FBC is equal to negative W the sine of alpha. Now since we're working with magnitudes here, I want to point out something. I'm going to put this in red so we can see this. This negative sign here means that we drew this FBC in the direction it's not supposed to. This FBC is actually in compression. So this element here, this BC is actually being compressed. That means the 2 points are actually it's being forced into one another and to shrink. If you get into solids, you'll understand more about it. But just knowing that that's in compression, that's all we can do. So now, from now on, in our understanding of it, we can say that the FBC is we rewrite this as FBC is equal to W the sine of alpha. And we've corrected it actually in the free body diagram. So that's how we can start, and that's the overall gist of using joints. Now, for planar geometry, like this structure here, this ABC structure, you only use sum of the force in the x, sum of the force in the y. There's no moments applied to the joint. If you're talking about finding the reactions of these, then you can apply the sum of the moments, but not in the joint. So you only have 2 equations, therefore you can only have 2 unknowns. So when you're doing these, make sure you look for joints first there's only can be 2 unknowns. Furthermore, it's very beneficial to know this if you're looking for if it's simple members or you're looking for something else. But mostly simple members, we can use the method of joints. We'll next talk about the method of sections, which will give us another strategy to find the internal workings of a structure. Good luck, have fun, keep learning.